Hi people, this video is on factoring sums and difference of perfect cubes, and then we're going to apply that to mixed factoring. All right, let's go. So as an introduction, we want to multiply the following expressions. So I'm going to expand this out. So I'm going to multiply x to x squared, which is x to the power of 3. Then I'm going to multiply x to negative xy. And since it's x times x, we get x squared with a y that tags along. And then we also have x times y squared, which is a positive xy squared. If I do that with the x, I also have to distribute the y through. So y to x squared is x squared y. Doesn't matter what order you write the multiplication in. Y times negative xy is negative xy squared. And then y times y squared is y to the power of 3. Now, what happens here? This goes away with this. These are like terms. These are also like terms, but they cancel each other out because there's a positive and a negative of each one. And I end up getting x cubed plus y cubed. And if you notice right here, this is a sum of perfect cubes. All right, so let's see what happens in our next expression. If I multiply this x through to this x squared, I get x to the power of 3. X multiplied by xy gives me positive x squared y. X multiplied by y squared is xy squared. Now I'm going to multiply this negative y through, so I get negative x squared y. Negative y to the xy, I get negative xy, and then negative y to y squared gives me negative y cubed. The same thing happens. This x squared y cancels with this negative x squared y. Sorry, this should have said minus xy squared. And then we also know that this xy squared is going to cancel out with this negative xy squared. So I end up getting x cubed minus y cubed, which is almost the exact same thing that happened here, except instead of it being a sum of perfect cubes, now we're going to have subtraction, or a difference of perfect cubes. So what does this tell us? This tells us that if I want to factor a sum of perfect cubes, it will look as follows. Because remember, factoring is undoing your multiplication. You're working backwards. You're finding out what times what gives us this expression right here. And then if I wanted to factor x cubed minus y cubed, it would look just like this right here. So what does this mean? If I want to factor a cubed plus b cubed, and I'm using a and b instead of x and y, just because that's typically how it's used, but you can use any variables you want. If I were to factor that out, it will look like a plus b, just like we have right here, x plus y, times a squared minus ab, just like we had minus xy, plus, instead of y squared, it will be b squared. So this right here is the factored form. And the difference of perfect cubes is almost exactly the same. It's a cubed minus b cubed, but instead of a plus b, it will now be a minus b. And then here, instead of a squared minus ab, it is now a squared plus ab plus b squared. And we need one of these to be positive, one of these to be negative, so that these terms that we have here to cancel out. And same thing here, one negative, one positive to get these terms here to cancel out. And this is also our factored form. So how do I apply this? So up here, we have 125y cubed plus 8. So since it's plus, we know it's a sum of perfect cubes. So just a reminder that when I want to factor this, it would become a plus b times a squared minus ab plus b squared. And that's what a cubed plus b cubed is. So I'm literally just copying this down on this page right here so I have it in front of me. So now I have to identify what the a is and what the b is. So if you can see here, the a cubed is this 125y to the power of 3. And the b cubed is this 8. So I'm going to write on the side right here, I want to figure out what a is going to be if I know what a cubed is. So here, if we know that a cubed is 125y to the power of 3, then we can cube root both sides. The opposite of cubing is cube rooting. So I would get a equals, and then right here, the cube root of 125 is 5 because 5 multiplied by itself 3 times gives me 125. And then the cube root of y to the power of 3 is just y. And then I'll do the same thing for the b. We know that b cubed is going to equal 8. So I'm going to say here b cubed equals 8. I'm going to take the cube root of 8, and then I end up getting b equals 2. So what I'm going to do here is I'm going to rewrite this as a cubed plus b cubed. So here I know that my a is going to be 5y. So this is 5y cubed. Isn't that the same thing as 125y to the power of 3? It sure is. So now here I'm also going to do the same thing with the 8. I'm going to do 2 to the power of 3, and that's what gives me 8 right here. So I know my a and my b. Okay, so now if you remember right here, the factored form looks like this. So it is going to be, just move this over here. Sorry, I know you can't do that on your paper. Just try to squeeze it in. So right here, I'm going to write this out as a plus b times a squared minus ab plus b squared. So again, so this would be a plus b multiplied by a squared minus ab plus b squared. Okay, so right here, I know that my a is 5y. So I can say that this is 5y plus, we know that b right here would have to be 2. And then here, I would say that this is 5y squared minus 5y multiplied by 2 plus 2 squared. And I'm just going to evaluate some of these things here. So I can say that this is just going to be 5y plus 2. There's nothing really to evaluate in my first bracket, but I'm going to figure out what each one of these numbers is. So I'm going to figure out what 5y squared is. And 5y squared means 5y times 5y, which is 25y squared. Here I've got 5y times 2, which is 10y, but because it's a minus sign, we're going to say minus 10y. And then here I'm going to do 2 squared, which is 4. So I'm going to put a 4 right here. And this is my factored form. If I were to distribute this all through here, all of this stuff right here through, I would end up getting this as my answer. So that is my factored form. Okay, so let's take a look at our next example. This time, we've got a minus sign. So we want to do a difference of perfect cubes. So I'm going to just write down the factored form right here. So we know a cubed minus b cubed, I'm just taking it from the previous page, is equal to a minus b times a squared plus ab plus b squared. Okay, so here I know that what I have written here is going to be something cubed minus something cubed. So I want to figure out what that something is. And me showing this workout on the side is just to help you see it, to help you understand what we're doing. You don't have to show the actual cube rooting if you can just figure out what it is. So here I know that a cubed is going to have to be equal to 27a to the power of 6b to the power of 12. So I'm going to take the cube root of everybody inside of here. So I end up getting a equals, the cube root of 27 is 3 because 3 times 3 times 3 is 27. Then I get a to the power of 2 because a to the power of 2 multiplied by itself 3 times gives me a to the power of 6. You can just divide this exponent by this root right here because this is always the denominator of your exponents. And then here I've got b to the power of 12, just divide that 12 by 3. So we know what a is. We know that this is 3a squared b to the power of 4, and that's being raised to the power of 3. Now let's figure out what the b is. So the b right here is b to the power of 3 is going to be 64c to the power of 15. So here I'm going to say b cubed is equal to 64c to the power of 15. I'm going to cube root both sides to calculate what this is, so I get b equals. The cube root of 64 is 4, because 4 times 4 times 4 is 64, and then I get c to the power of 5, because 15 divided by 3 is 5. So this right here is 4c to the power of 5. So now let's go ahead and get ready to do our factoring piece right here, now that we know what a and b are. So we know it's going to be a minus b multiplied by a squared plus ab So it's going to be something times something, and then plus b squared. So I'm going to say right here plus that b squared. Okay, so we know that a is going to be, I'm going to zoom in on this a little bit so you can see this a little bit more clearly. We know this is going to be 3a squared b to the power of 4, and that's going to be minus the b, which we know is 4c to the power of 5. And then that's going to get multiplied by whatever you get when you square the a. So this is going to be 3a squared b to the power of 4 squared plus, again, the a is 3a squared b to the power of 4. That's going to get multiplied by b, which we know is 4c to the power of 5 plus 4c to the power of 5 squared. So right here, there's really nothing I can do with this first expression. So I'm going to keep it as is. And then in my second expression, I'm going to actually square this. So 3 when I square it is 9. A squared when I square it is a to the power of 4. And b to the power of 4 when I square it is b to the power of 8. Okay? Here, I'm going to multiply these two together. So 3 times 4 is 12. And then I just have a squared, b to the power of 4, c to the power of 5. And then lastly, I'm just going to square this. So 4 squared is 16. C to the power of 5 when I square it is c to the power of 10. And then this right here is my factored expression. Okay, so really, just to recap, you just have to figure out what a and b are, and then you just plug it in into this piece right here, and then you are good to go. We're going to go through this list of questions that we have here. So we've got 1, 2, 3, 4, 5, 6, 7 questions we're going to ask ourselves whenever we factor. There are more questions now than there were when we originally started this course. So let's go through and answer these questions for question number 1. So the first question says, is there GCF? So when I look at all of these terms right here, I can see that there's an x in common. So the first thing I'm going to do is factor out that x. So when I do that, I end up getting x to the power of 3 minus 2x squared minus 5x plus 6. Okay? Then I'm going to ask myself, is it a difference of perfect squares? And in order for it to be a difference of perfect squares, we need to have two terms, subtraction and perfect squares, which we don't have. We have 1, 2, 3, 4 terms right here. So I'm not going to factor this as a difference of perfect squares. The next question is it a sum or a difference of perfect cubes? In order for this to be a sum or difference of perfect cubes, we still need to have two terms. It doesn't matter if it's addition or subtraction this time because we can do both. And we need to have perfect cubes. Okay? So when I look at this right here, it's also not a sum or difference of perfect cubes because I don't have just those two terms. So then the next question is it a trinomial that I can factor? Well, it's definitely not a trinomial because there are 4 terms. So then I'm going to ask myself, can I factor by grouping? And when I look right here, strategically, if I see here, when I factor this by grouping, I would group these two together. There's an x squared in common. Don't write this down, but I can see, hopefully in my head, that I would have x minus 2 left over. Here, there's nothing in common. I would just factor out a negative 1. I'd have 5x minus 6 left over. There's nothing in common between this and this, so this is not a factor by grouping question, even though there are 4 or more terms, 4 terms specifically. So now, I'm going to ask myself, can I factor this using the factor theorem? So in order for me to see if I can factor this using the factor theorem, I got to guess and check some numbers. So I'm going to go into Desmos and I'm going to type in f of x is equal to, and then I'm going to go back to my main right here and type in the expression that was inside of my brackets. So I'm going to type in f of x is equal to x cubed minus 2x squared minus 5x plus 6. The nice thing here is that my leading coefficient is 1, which means that all my factors that I'm going to be using are not going to be fractions, because when I divide anything by 1, because those are the only factors of 1, I still get the same number that I originally had. So now I'm going to look for factors of 6. So some factors of 6 would be plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. So let's go ahead and do f of 1. I get a remainder of 0. This is awesome, so I can factor this out using synthetic division. So over here on the side, I'm going to write out right here 1, -2, -5, and 6, and I'm going to do my synthetic division for it. And I'm just going to separate this right here so I have space. So right here, I've got a 1. 1 times 1 is 1. -2 times plus 1 is -1. -1 times 1 is -1. -5 minus 1 is -6. -6 times 1 is -6. I get a remainder of 0. This is promising. Awesome. So now we can say that this is x times x minus 1 because I got this x minus 1 from this right here. And then what I have left over here is my remainder, 0 degree or constant, first degree, second degree. So this is x squared minus x minus 6. And now I can just go through and I can see that I can factor this easily. So this would be x minus 3 and x plus 2. Because -3 and 2 multiply together to give me -6, and -3 plus 2 adds up to give me -1. So then I get x minus 1 and x. I just copy that down. Now I just have to ask myself, is my expression completely factored? How do I know if it is or not? I look at each factor separately. I can't do anything more with x. I can't do anything more with x minus 1. I can't do anything more with x minus 3, and I can't do anything more with x plus 2. So this is my completely factored expression. All right, people. So in our next example, I'm going to go through this whole list right here. So we're taking a look at number 2. So the first question I'm going to ask myself is there GCF? So is there anything in common with all of these terms? And there's nothing in common with all of them. So I don't have a GCF. Then I'm going to ask myself, is it a difference of perfect squares? Which it's not, because it's definitely a lot more than 2 terms. Then I want to know, is this a sum or difference of perfect cubes? Also not, because it's definitely more than 2 terms still. So then I want to know, is this a trinomial that I can factor? Which it's not, because it's not 3 terms. So then the next question is, can I factor by grouping? And if I was able to factor by grouping, I would have to have an even number of terms, more than at least 4. So I need to have at least 4 for me to be able to factor by grouping. Otherwise, it's just a GCF question. So when I look at this right here, I definitely have an even number of terms because I can group these together, group these together, group these together. So I'm going to try to see if I can factor by grouping, see if there's anything in common. So in my first group right here, I can see that the largest exponent that I can pull out for that x would be x to the power of 4 without going over this right here. So my GCF here would be x to the power 4. When I factor it out of this guy, I get an x left over. And when I factor it out of this term, I have a 4 left over. Okay, then I'm going to take a look at my next group. And I can see here that, first of all, my leading coefficient is negative, so I'm going to factor out a negative. There's a 2 and an 8 here, and they're both divisible by 2. And then for the x cubed and x squared, the greatest common factor would be x squared. When I factor it out of -2x cubed, I get positive x. When I factor it out of -8x squared, when I divide this by this, I get a positive 4. Now, in our last group right here, by the way, this is looking quite promising, isn't it? In our last group, there's nothing in common. So I can only factor out a 1. But when I factor out the 1, I can see that this is also in common with what I have inside of here. So because all of these have an x plus 4 in common, I can factor out the x plus 4. And then I can say that I have x to the power of 4 left over minus 2x squared plus 1. Okay, so I was able to factor by grouping. So now I want to look and see what I have inside of my brackets here. So inside of my brackets here, for my first bracket that I have here, I've got x to the power of 4, I've got x plus 4. So I'm going to look at this x plus 4 and go down my list again. Okay, so I can't show both the list and x plus 4 on the screen, so I'm just going to show the list. So x plus 4 has no GCF. It is not a difference of perfect squares because there's no subtraction. It is not a sum or difference of perfect cubes because we do not have perfect cubes. It's not a trinomial that I can factor. I can't factor by grouping. I don't want to use the factor theorem because it's a linear factor. And to be honest, this is a linear factor that has nothing in common, so I cannot factor this further. So now let's go ahead and take a look at this next expression that we have here. So let's go down our list again. Is it a GC? Is there GCF? No. Is it a difference of perfect squares? Nope, because it's more than two terms. Is there sum or difference of perfect cubes? Nope, because it's more than two terms. Is it a trinomial that I can factor? Which it is, because there are three terms here. So I'm going to try to factor this trinomial that we have here. So I know this times this would give me x to the power of 4. So I will use x squared and x squared. I also know this times this gives me 1. So I would use 1 and 1. And I want this x squared and this x squared to collect together to give me -2, which is possible if I have both negative x squareds, which means that I would have a minus sign here, a minus sign there. Then I copy down this x plus 4. Then I start all over again, but I don't have to worry about the x plus 4 here because we've already figured out I can't factor that further. However, I do have this x squared minus 1, and I can recognize that this is a difference of perfect squares. Why? We've got subtraction, we have two terms, and we have perfect squares. So when I factor this, I would get x plus 1, x minus 1 right here. When I factor this, I would also get x plus 1, x minus 1. And then I copy down this x plus 4. And I look and see, can I take any one of these factors any further? I cannot. But I'm going to say that I have two sets of x plus 1, and I also have two sets of x minus 1. So I'm going to write this out as x plus 1 squared, and I'm going to write this out as x minus 1 squared, and then I'm just going to put this x plus 4 in front, and boom, there's my answer. All right, people, number 3 is the last one we're going to do together in this video, and then we'll do number 4 in class together. So the first question is there a GCF? So if I take a look at what I have right here, I'm going to look at each one of my terms and I'm going to see, is there anything in common with every single one of my terms here? And there's nothing in common. So there's no GCF. So then the second question I'm going to ask myself is it a difference of perfect squares? Nope, it's not two terms. So I can skip this step and this step because neither one of these will work because that we need two terms for that to work. Is it a trinomial that I can factor? Not a trinomial. Can I factor by grouping? Well, I do have an even number of terms that are more than 2, that are 4 or more. So I can try to see if I can group this. So I'm going to take these two right here, and I'm going to see that they're both divisible by a squared. So when I do that right here, I've got p to the power of 3 plus q to the power of 3 left over. Then I'm going to look at my second group right here, and I'm going to take out a negative, and I can see that there is a b squared in common with both of these terms. So when I factor that out, I get p to the power of 3 plus q to the power of 3. When I do this, I see that there is a p to the power of 3 plus q to the power of 3 in common. And when I factor it out of here, I get a squared left over. And when I factor it out of here, I get a minus b squared left over. All right, awesome. We start fresh now. So I'm going to take a look at this p cubed plus q cubed right here. Is there GCF? No. Is it a difference of perfect squares? No, because we don't have subtraction and we don't have perfect squares. Is it a sum or difference of perfect cubes? It sure is a sum or difference of perfect cubes because we have two terms. We have perfect cubes. So just a reminder that if I were to factor a sum of perfect cubes, we know that a cubed plus b cubed is going to be equal to a plus b times a squared minus ab plus b squared. So in this expression right here, the a is like p, so we can say a is the p, and the b is like q, so we can say b is q. So here I'm going to say that this is p plus q, because it's a plus b, times p squared, a is p, minus ab would be pq, and then b squared would be q squared. Okay, then I'm going to take a look at what I have right here as well. This right here, I can recognize that that's a difference of perfect squares because there's subtraction, there's two terms, and they're perfect squares. So right here, this would become a plus b times a minus b. Okay, then I want to take a look at each one of my factors separately. So for my first factor that I'm looking at here, this p plus q, I can't factor this further. It's literally just a linear relation. There's no GCF, there's no perfect squares, there's no perfect cubes. It's not a trinomial. I can't factor by grouping. I can't use the factor theorem. This one's a tricky one because this one right here is a trinomial, yes. However, if I could have factored this any further, then that would be part of my definition of a perfect cube. But this is not possible because the only way that we could factor this right here, you don't have to write this down, would be if I have a p, a q, and a q. But because this would give me pq and this would give me pq, these two together would become either 2pq or 0pq, but there's no way I can get negative 1pq from that. So this expression that we have highlighted here cannot be factored any further. This a plus b is a linear factor, can't factor it any further. A minus b is also a linear factor, can't factor it any further. So this is my final answer and the end of this video. If you have any questions, let me know. Otherwise, I'll see you in class. Bye.